What would actually kill you first on the moon? It's not just the classic astronaut movie scenario. The lunar surface offers a buffet of creative demises. Forget oxygen deprivation, that's just a starting point. Your body, unprepared, would face a gauntlet of extinction-level events, each more eager than the last to make you a permanent, frozen monument. But which one wins the grim race for your ultimate inconvenience? Engineers are betting on solutions, but the moon keeps dealing new, often lethal, cards. Most assume the airless void is the instant killer. And they're not entirely wrong. Without pressure, fluids boil. Your lungs would collapse in seconds, eardrums burst. But here's the kicker, you wouldn't explode. Your skin is surprisingly resilient. You'd bloat, turn purple, and within 90 seconds, lose consciousness as oxygen fled your blood. The cold vacuum ensures your body remains intact, a perfectly preserved curiosity for future archaeologists. Pressure suits are not just for show, they're bespoke coffins, keeping the outside out and the inside in. If the vacuum doesn't get you, the universe's own particle accelerator will. The moon has no atmosphere, no magnetic field. That means direct exposure to galactic cosmic rays and solar particle events. Think of it as a constant, invisible rain of high-energy particles tearing through your DNA. Acute radiation sickness would be a slow, agonizing descent, symptoms appearing hours to days later. Cancer risk skyrockets. Engineers design habitats with thick shielding, but every gram of protection adds to launch cost. You can run, but you can't hide from every atom. The moon's day and night cycles are brutal. With no atmosphere to trap or distribute heat, temperatures swing wildly. Daytime can hit 120 degrees Celsius, enough to bake you. Nighttime plummets to a chilling minus 173 degrees Celsius, enough to freeze you solid. Your suit's life support system works overtime, fighting a losing battle against thermal extremes. Engineers use multi-layer insulation and internal heaters and coolers, but these are energy guzzlers. One system failure, and you're either a crispy astronaut or a human icicle. Pick your poison. Think of it as cosmic buckshot. The moon, lacking an atmospheric shield, is constantly bombarded by micrometeoroids, tiny particles traveling at incredible velocities. While large impacts are rare, even a grain of sand at 20 kilometers per second packs a punch. It could puncture your suit, your habitat, or worse, a critical oxygen tank. Engineers design habitats with multiple shielding layers, often using regolith itself as a protective barrier. But a rogue pebble with an attitude could still ruin your lunar vacation faster than you can say decompression. Perhaps the most underestimated killer, lunar dust. It's not like Earth dirt. Apollo astronauts called it talcum powder with attitude. It's electrostatically charged, abrasive, and razor-sharp, a result of millions of years of micrometeoroid impacts. This fine, jagged dust gets everywhere, clogging mechanisms, scratching visors, and potentially causing respiratory issues if ingested. It's a silent, insidious threat that could disable critical equipment, leading to a cascade failure. Engineers are developing dust-repelling surfaces and advanced air filters, but the moon's grit is relentlessly invasive. Survival hinges on resources, and water is life. The moon does have water ice, especially in permanently shadowed craters, but extracting it is an engineering nightmare. Transporting massive amounts from Earth is economically unfeasible. Without a reliable, self-sustaining water source, hydration becomes a critical, daily struggle. Dehydration can rapidly impair judgment and physical ability, turning minor issues into fatal errors. Engineers are racing to perfect in situ resource utilization, turning lunar ice into drinkable water and breathable oxygen. But for now, every drop is precious. Imagine needing urgent help, but your cries take seconds to reach home. The moon's distance from Earth means a communication delay of 2.5 to 3 seconds round trip. In an emergency, these seconds are deadly. It complicates medical advice, critical system diagnostics, and rescue coordination. Every decision must be made with independence and self-reliance, with no immediate backup from mission control. This isn't just an inconvenience, it's a psychological and operational barrier that forces extreme autonomy. No instant gratification, only instant peril. While not an immediate killer, the Moon's 1/6 gravity poses chronic threats. Long-term exposure leads to bone density loss, muscle atrophy, and cardiovascular deconditioning. An astronaut could become too weak to perform tasks or even survive readapting to Earth gravity. This gradual debilitation undermines all other survival efforts. Exercise regimes and specialized medical countermeasures are crucial, but the human body simply isn't designed for perpetual featherlight living. It's a slow, insidious erosion of your physical being, turning you into a lunar noodle. All lunar survival systems, life support, heating, communication, water extraction, rely on power. Solar panels are effective during the day, but the 2-week-long lunar night demands robust battery storage or radioisotope thermoelectric generators. A major power failure during the frigid night would initiate a rapid cascade of system shutdowns. Without heat, water freezes. Without life support, oxygen depletes. You'd quickly be exposed to a hostile environment your suit can't handle alone. It's the ultimate sun-plugging scenario, with terminal consequences. So, what actually kills you first? While the vacuum is quickest to incapacitate, the insidious, long-term threats like radiation exposure and the abrasive regolith chip away at your chances. A catastrophic suit puncture from a micrometeoroid or a critical power failure during the lunar night could be the final straw. But perhaps the truest killer is the accumulated probability of multiple systems failing, of human error meeting an unforgiving environment. On the Moon, survival isn't about avoiding one death, it's about delaying the inevitable. And engineers are still writing that delay, one ingenious solution at a time.